Hey folks, today I've uploaded this video and it is aimed at taking you through a whistle-stop kind of introduction tour on magnetism. So that includes magnetic poles and magnetic field lines. Now this is the same PowerPoint that I would use in a lesson, so I'm not going to go through absolutely everything that's on the screen at the moment. Some of that is for students when they walk into my room, just telling them what we're going to discuss and what they need to be able to do by the end of the lesson. I don't think it's worth going through that at the moment. So what we're going to look at is essentially a basic bar magnet. And a bar magnet has the following features. It's permanent, so it won't lose its magnetism, at least not quickly. Okay, so it's not like an electromagnet that can be turned on and off. This is a permanent magnet which retains its magnetism for a really long period of time. It has two poles. These are the things that we see at the end. So we have the North Pole and the South Pole. So magnets exert an attractive force on magnetic metals, and there's three magnetic metals that we need to be aware of. It's iron, cobalt and nickel. Now what's worth bearing in mind is that alloys, so metals that are made of more than one type of metal, are not necessarily going to be magnetic. So steel, even though it contains iron, depending on what it's mixed with, won't necessarily be magnetic. Both the North and the South Pole attract magnetic metals equally. So the North Pole is just as attracted to the iron as the South Pole would be. That makes no difference. But magnets can behave differently around each other. So like poles, and what we mean by that is poles which are the same, so south and south or north and north, they actually repel each other, and that means they push each other away. But unlike poles, so poles which are different, so if we add a south to a north or a north to a south, these will be attracted to each other, so they actually pull each other in. It's an attractive force. Here we've got a question where it would ask you to tell the difference between three unmarked metal bars. Two of them are magnets and one of them is not. How would you be able to tell which two were the magnets and which one was the non-magnet? The trick to this one is that if you test the end of each bar with the end of each other bar, there's only one combination where they would repel each other, and that's if you got the like poles of the magnets to try and go near each other. Wherever you see repulsion, you have to have two magnets, okay? Because a magnetic metal, which isn't a magnet but is still magnetic, would be attracted to all parts of a magnet. You can never get an unmagnetized piece of magnetic metal to repel from a magnet. It's always a force of attraction. So wherever we see repulsion, we definitely have two magnets, okay? As a little side note, I see quite often come up on questions, we have a magnet, a piece of iron and something else like a piece of copper or aluminium. It's a variation on the same question, but you'd identify the piece of aluminium or copper because it's not magnetic. It won't stick to the magnet. So all magnets have what we call magnetic field lines, which are these invisible lines of magnetism that surround the magnet. Now you may have seen this before. We can see in the picture where if we use very fine pieces of iron, which we call iron filings, strangely enough they're filed off pieces of iron. Iron, being a magnetic metal, will allow itself to be aligned in the magnetic field. Okay, and what we see is that the metal filings, these iron filings, will align themselves along the lines of the field. So you can see them coming out at both of the poles, so out of the South Pole and out of the North Pole, and we can see them kind of looping around in between. And we see the really high concentration of iron filings. Most of them will stick at the poles, so at either end, and we see that kind of looping pattern going round from south to north, or from north to south from the magnet, and that's kind of showing us physically where the magnetic field lines are. Magnetic field lines always go from north to south, so they come out of the North Pole and they go in to the South Pole. And what's really important to remember is that at the poles, so at the North Pole and the South Pole, these magnetic field lines are really close together. This means that's the strongest part of the magnet. Okay, so that will exert the strongest magnetic force. Whereas in the middle, you can see the lines are further apart. So that's actually the weakest part of the magnet. In the diagram on the screen, we can see what happens when we put magnets together. So where we put two like poles together, so on the left we've got repulsion, where north is next to north. You can see the magnetic lines will never cross each other. So they will push apart. They're diverted away from each other. But with attraction, where we have north to south, we know that the magnetic field lines like to go from north to south, so they will go from the north of one magnet to the south of the other, and that causes a force of attraction. There is another method that we need to be aware of for plotting our own magnetic field lines, and for this we use something called a plotting compass. It looks very similar to the sort of compass you might have used when finding your way around outdoors. So a plotting compass will always point to the south pole of a magnet. It's basically a tiny little bar magnet inside that circular container you can see there, and we use these to draw the magnetic field lines, and I'll show you exactly how we do that. It's very simple. So we place the compass at any pole, it could be north or south, and we plot the ends of the needle. Then we start to move the compass around so that it's always next to the previously plotted point. And it's simply a question of joining those plots together. Now, the video on here is actually relatively quick, so we can play it again. So we place the compass at any pole, and we plot the ends of the needle. We then move the compass around so that it points to the last plotted point, and we plot again and repeat. Okay, so here we go, one more time. And it really is a very simple process. It's something that they quite like to ask you about on exams. And finally, one last point to note. The Earth is essentially a giant permanent magnet, and that's due to the fact it has an iron core, and we know iron is a magnetic metal. But the Earth's magnetic field is changing, and it's most likely due to the movement of the iron core. Now, there is evidence for this. One of the most common and easily understood is the change to migration patterns of birds. So we know that when birds migrate to get to warmer climates, they tend to use these magnetic field lines. Somehow they're able to sense them, and they use them for navigation, a bit like a GPS. And we've noticed changes to the flight paths of these birds and the directions in which they are travelling. And that's because their GPS, if you like, their ability to sense these magnetic field lines is showing that the field lines are changing direction. So we're seeing the birds move in different directions during mass migrations. And essentially that is our whistle-stop tour through our sort of introduction to magnets. Now, if you found that useful, obviously you can watch the video again, but if you're watching this from a teaching point of view, you can download this presentation and some questions associated with it with a mark scheme from tes.com. It's only £1, okay, not very much at all. You can help a poor teacher out, and that will enable you to use this presentation and add to it and do whatever you want with it, as well as having access to the questions with the mark scheme. You don't have to be a teacher to join, anyone can, so I'd highly recommend you do, and there's lots of other useful resources on there as well. Anyway, thanks for watching, and I hope it was useful, and we'll speak to you next time.